Welcome back. So, we are going to resume our discussions, and in this session we are going to compare embedded systems and general purpose computing systems. So, the first difference is that embedded systems are dedicated for specific tasks. They may be one task or there may be few tasks, there may be more than one task, but that number is fixed. As against a general purpose computing system where you can put any applications, you can add applications. Embedded systems are different from such general purpose systems. As an example, if I have a microwave oven, the embedded computer in the microwave oven is designed only to cook food. I can't reprogram it and expect it to wash clothes. That is the kind of glaring difference that I have between an embedded computer and a general purpose computer. The second difference is that embedded computers can be implemented using a wide variety of processors. As you saw, a processor, a microcontroller smaller than a grain of rice, and on the other extreme a big microcontroller more than an inch square. But when you look at general purpose computing devices, usually you use the highest performance processor that is available. The third difference is that embedded systems are cost sensitive. What is the meaning? Because you are buying a product, you are not buying a computer. The embedded computer that forms part of that embedded system gadget carries a small fraction of cost, and therefore, embedded computers, embedded systems are very cost sensitive. And the fourth difference is that embedded systems are supposed to offer and work under real time constraints. The meaning is that whenever there is a input change, environmental change, the embedded systems are supposed to react to that change and provide an output in a timely fashion. If there is delay in producing the output, it may lead to fatality, it may lead to loss of life. As an example, if the embedded computer which is flying an aircraft and the pilot wants the aircraft to climb and the embedded computer does not perform appropriately and keeps on flying at the same level, it may lead to a crash. Now, you do not expect such a behavior out of a general purpose computing system. Oftentimes you may have noticed that you press a key and your laptop or desktop does not respond. It is alright because it is not going to kill anybody. And so, there is vast difference between the expectations of an embedded computer in terms of requiring a real time response. The fourth difference or fifth difference is that embedded systems are designed to operate in an extreme environmental conditions. Take the example of a missile system. That missile could be launched from glacier environment or it could be launched from deserts, and they must perform. Usually embedded systems run out of a ROM, meaning that the program that is stored in the embedded computer is stored in a ROM, that is read only memory, a permanent memory. But oftentimes, not oftentimes, most of the times the program that runs on your desktop or laptop computer is running in the RAM. Yes, a desktop or a laptop system also has a ROM which is used at the beginning when you power on your device, and that program is called a boot up program called BIOS, basic input output system. Once that completes execution, the control is transferred to the operating system on the hard disk and then to the program that you would like to run. These programs are loaded in the RAM of the general purpose computing system. So, that is a vast difference between how an embedded system operates and how a general purpose computing system operates. Another difference is that embedded systems have resource constraints. What are resources of a computer? The computational capability is a resource. The way the embedded system or the computer communicates with the outside world is a resource, and you see when you have a general purpose computing system such as your laptop or desktop, it has many ways of communicating with the outside world. It has Ethernet, it has Wi-Fi, it has Firewire, it has USB and so on. But does your microwave have Ethernet connection? Can you control it with your phone through Bluetooth? Most probably not. Although in recent times there are certain examples of such embedded applications with connectivity, but that connectivity is based on the requirement, not because you want to flaunt that your computer has so many ways of communicating with the outside world. So, embedded systems have resource constraints. There are examples of, for example, a washing machine which is called IoT washing machine. That washing machine can communicate with the outside world through internet, and the purpose is not that you would want to control this washing machine sitting in your office, but when the washing machine is operating at home and encounters loss in performance, it can communicate that to the service provider, the maintenance guy, so that they can come and provide preventive maintenance before the washing machine actually stops working. So, this is an example where you have a communication protocol, communication link on your embedded device, but it is out of necessity as a feature, not because you want to say that your washing machine has so many ways of communicating with the outside world. Embedded systems are infrequently reprogrammed. What is the meaning? That once you load a program in an embedded application, you do not ever change it. You do not change it most of the time, and in most cases you do not ever change it. But in a general purpose computing device, every time you run an application, a new application, you are reprogramming that device. How many times have you encountered a situation that somebody has come to your home saying that they would like to upgrade the firmware of your washing machine? I have never encountered it. It does not happen. And so, that is the meaning of this point, that embedded systems are infrequently reprogrammed. Embedded systems have hard reliability and correctness constraints. All computers must operate correctly, but embedded systems have an additional responsibility, that they must continue to provide service reliably. Not all, most of them, many of them, some of them. Why? Because failure to do so may lead to loss of life. As an example, medical devices like an X-ray machine, you do not want the computer in the X-ray machine to fail, and it may give needlessly high dose of X-ray to the patient under the X-ray machine. In an aircraft, you do not want the computer flying the aircraft to fail, leading to loss of life, and so embedded computers are expected, some of the embedded computers are expected to have hard reliability requirements. Okay, now that we have seen major differences between embedded computers and general purpose computing devices, it is time to go through certain terminologies that we use, and for many of you or some of you, it may be a repeat of things that you already know, but it does not hurt. So, the first terminology is, what is a computer? A computer is nothing but a system which has a CPU, that is a central processing unit, memory, and input output ports. Let me draw a diagram to illustrate it. So, this is your CPU, this is your memory, and usually you would require two types of memories. One is the ROM, which stores your program, the other is the RAM, which has which you use for variables, and then you would have certain IO devices, maybe an input device and an output device. Let me erase this and write it here. And how does the CPU communicate with these devices? Through buses. These buses are for data and for address, and another set of bus is what we call as the control bus, which tells whether you are reading information or writing information, and all these So, this is the diagram for a computer. Here is the CPU, ROM, RAM, that is memory, and input output ports. The second terminology is a microprocessor. A microprocessor is nothing but a CPU on a single chip. How did it happen? In the 50s and 60s, the CPU was made with discrete components or discrete integrated circuits in the 60s. In 1971, a startup at that time that was called Intel, and today Intel is a giant, made an interesting device. What it did was it integrated the functionality of a CPU on a single substrate of silicon. What does a CPU entail? A CPU has 4 components. It has so a CPU has control unit, it has registers in which temporary information is stored, it has a ALU through which it can perform mathematical and logical operations, and it has a bus interface unit through which the CPU can communicate with the outside world to the memory and to the IO ports. Now, all these were originally in the 50s and 60s implemented using discrete components, discrete integrated circuits, and what Intel did in 1971 is that it integrated all these on a single substrate of silicon and made a IC out of it, and that IC was named 4004 microprocessor, and the term microprocessor came about. So, that is the definition of microprocessor. Then what happened? When people started using a microprocessor to create computers, it drastically reduced the size of the computers. Earlier, in the earlier days, the computers would probably fill half a room, but now suddenly you could fit the entire functionality of a computer on a single printed circuit board, and such computers were called microcomputers. So, a microcomputer is nothing but a microprocessor plus memory plus IO devices on a single printed circuit board. In the same scalability fashion, the entire functionality of the microcontroller people thought could be integrated on a single piece of silicon, and what happened? It led to a microcontroller. So, a microcontroller is nothing but a microcomputer on a single chip. Who did that? It turns out incidentally that the world's first microcontroller was in 1974. It was TMS 1000, and this was by a company which is incidentally also supporting our program, this course here, Texas Instruments. This was a 4-bit microcontroller. I am going to use this terminology mu-c to indicate that it is a microcontroller. Now, obviously, you may have heard of Moore's law that says that it is not really a law, it is an observation that every 18 months, that is 1.5 years, the number of components, number of transistors that you could integrate on a piece of silicon would double. Now, what would you do with these increasing number of transistors? Of course, you could fit more and more functionality on a single piece of silicon, and so this is the reason why you had a microprocessor, and from the microprocessor you had a microcontroller. What next? Now, when you use a microcontroller in any control or embedded application, apart from the microcontroller, here is your microcontroller, you still need analog components. For example, I may have a certain sensor, and the output of this sensor may need to be amplified with the help of an operational amplifier, right. And so, I need to provide a certain amount of gain. So, I am going to put components like this. This is going to, so this is my sensor here. This sensor, the output voltage of this sensor is going to be amplified with this, maybe with another op amp circuit. I am going to amplify, I am going to filter this signal in some way, and eventually feed it to the microcontroller, maybe to the ADC input. We will come to more details about this ADC input, but you see if I have to design a system out of a microcontroller, apart from the microcontroller which has already integrated so many components on a single integrated circuit, I still need these additional components. These are analog devices, analog components, and it is very difficult to make analog devices and program them. Meaning, if I have an amplifier, how do I write a program to change the gain of the amplifier? How do I write a program to change the cutoff frequency of a filter, or the gain, or the slope of that filter, or the order of that filter? It is very difficult, but interestingly that also happened, and that led to a definition called system on chip. A system on chip in this context is a microcontroller plus analog components which are programmable, and this was by a company called Cypress Semiconductors. What they did was they added microcontroller plus analog building blocks, and you could change the functionality of these analog building blocks by merely writing a program. So, you could decide that today I want the analog building block to function like an amplifier with a certain gain, or change the topology of the amplifier to be inverting or a non-inverting or a differential amplifier, or you want that analog building block to be of to provide functionality of a filter, in which case what is the cutoff frequency, what is the topology of that filter, do we want it to be of the low pass, band pass, high pass, band reject, notch, and so on. And so, this provides great functionality. And so, having a system on chip which integrates not only the microcontroller, but also analog building blocks will reduce the size of the eventual system to a single integrated circuits, and that is a great improvement, and we will see how. Here is an example of a single board computer using a microprocessor. You see a single printed circuit board has been used. This is just to show you how from the earlier times where the entire computer would be a big device has been shrunk to the size of a single PCB. Anyway, now in the context of system on chip, I want to clarify that there are certain interpretations of this system on chip. One is that system on chip is nothing in our context of embedded systems, that system on chip is a microcontroller plus programmable analog components on a single substrate of silicon. But in general, when people refer to this term system on chip, they mean probably a microprocessor or a microcontroller together with some custom functional units units on a single piece of silicon, and that they mean system on chip. And so, it is very important to know the context. Is the person talking about an embedded application where it might mean a microcontroller and analog components, or in a general context. Anyway, now we come to this point, we have mentioned this earlier, that a microcontroller is a popular method of implementing the embedded computer. But what are the other methods? We must be aware of them. So, the first method by which we can implement an embedded computer is through a general purpose processor, meaning a microprocessor for example. Another method is to use what is called as a application specific processor. What are the examples of application specific processors? Well, a microcontroller is an example of application specific processor. Also a digital signal processor, which is a specialized processor which can perform digital signal processing more efficiently than it is possible with a general purpose processor. And the third method is what we call as single purpose computer. I would like to elaborate on these three approaches. In a general purpose processor, basically you are saying I am going to use a microprocessor, but a microprocessor is only one part of the entire ecosystem of a computer. Apart from the microprocessor, what you need is you need external memory of the type of ROM or of the type of RAM, and then you are going to need ports. And so, what it would lead to is that it will not remain a very efficient from a size point of view. It will not be a very efficient implementation, because a microprocessor offers certain amount of memory. That is, if for example let us write this down, if my microprocessor has certain amount of data lines, let us say this is data, and common examples are 8 or 16 bits or 32 bits. It also has, the data is by the way bidirectional, it could have it would have address lines. Let us say it has 20 address lines. If it has 20 address lines, that means it can access how many memory locations? 2 raised to power 20, which is equal to 1 0 4 8 5 7 6 memory locations, that is 1,000,000. Now, it can communicate or it can talk to 1,000,000 memory locations. It is up to you to provide the requisite amount of memory. Maybe you realize or you anticipate that your application is going to need 16 kilobytes of ROM, another 16 kilobytes of RAM. So, you have to add appropriate memory devices to fulfill the requirement. So, this would lead to a physically large system as far as implementation is concerned. On the other hand, when you choose to have when you choose to implement that application using an application specific processor such as a microcontroller is going to have a microprocessor, that is a CPU on the on that silicon substrate. Apart from the CPU, it is also going to have RAM and ROM in various types of a fixed amount. Maybe it has 8 kilobytes of ROM and 8 kilobytes of RAM. If you find that this amount of memory is suitable for a particular application, it may make a better sense to use an application specific processor such as this microcontroller to implement that system, because it would lead to reduction in size and reduction in cost. It would improve reliability because there are less number of components to solder. So, it would be a more reliable system, and so oftentimes you would implement your application with a microcontroller as an example of application specific processor. But that is not all, you can also implement the same system with a single purpose computer, and I am going to illustrate these three approaches using certain block diagrams. Now, when I implement an application using a general purpose processor, here I have drawn a block diagram. This is an alternative view to understand what is the meaning of a microprocessor. Now, one way to understand microprocessor which we have seen is that a microprocessor is nothing but a ALU, registers, control logic and bus interface unit on a single piece of silicon. That is to indicate these 4 components as functional units. There is an alternative view to understand how a computer works, and which is through this diagram, that we have 2 blocks, one is called the sequencer and the other one is called the data path. The sequencer consists of the control logic, it has instruction decoder and a program counter, and the sequencer talks to an external memory device such as the ROM or EEPROM or other types of memory devices. And the reason why you can implement any different type of application is by changing the contents of the program. The sequencer understands the instructions, and based on the sequence of these instructions which you as a user have to write, it can implement a different application. It does that by providing inputs to the second part of the building block, which is the data path, and data path consists of the registers for storing temporary values, and the registers feed the arithmetic logic unit. So, essentially the sequencer and data path form the CPU. This CPU could be in the form of individual ICs or it could be in the form of a microprocessor, and that is the alternative view to look at a general purpose processor. You are going to need external program memory and data memory. Program memory feeds the sequencer, data memory is connected to the data path so that you can store variables. So, while this is the this is the block diagrammatic approach of alternative approach of looking at the general purpose processor, let us see if we were to implement an application using a general purpose processor, what would it look like. And for example, we have a anyway before we come to that example, let me show you the block diagram for a application specific processor also. This application specific processor also has a sequencer which consists of the control logic, it has the instruction decoder and the program counter which is connected to the program memory. The program memory is populated, is filled up with instructions by you as the designer. The sequencer reads the contents of program memory and executes whatever that program memory instruction expects you to do, and then controls the operation through the data path, which consists of registers and a ALU. Now, in the previous case, the ALU was a general purpose ALU, but for a application specific processor, it may be a custom ALU, meaning you would want to do certain operations more often, therefore, you provide that arithmetic logic unit with that additional functionality. Like in a DSP, a DSP operation requires repeated multiplication and addition of numbers, and so in a DSP you have a ALU which has a feature called MAC, multiply and accumulate, right. Apart from that, the program memory and data memory could be integrated on the same chip. If you see this block diagram, I have drawn a dotted line around the components to indicate that these 4 block diagrams are actually could be integrated on a single piece of substrate to give you a more efficient implementation. Now, let us look at the block diagram of a single purpose processor, which consists of a sequencer which is implemented as a state machine. State machine is another word for finite state machine or a state machine. It is usually implemented with memory building blocks such as a flip flop. That sequencer communicates with data processing element. Now, in contrast to the data processing elements, that is the data path in a general purpose processor or application specific processor, where you have registers and ALU to perform those operations, nothing is fixed for the data processing elements in a data path of a single purpose processor. Why? Because the purpose is fixed and it is only one purpose that you want to design it for. You put appropriate data processing elements, which could be decoder, adder, it could be an encoder, multiplexer, demultiplexer and so on and so forth. And of course, the data path would want to store some information, so it has memory usually in the form of a RAM. And so, when you design a system which is expected to perform only one task, and you have specifically designed this hardware just to do this and nothing else, this would be called a single purpose processor. And any application could be implemented in any of these 3 ways, and it would depend on you as a designer of embedded systems to decide whether you want to go through a general purpose processor route, or do you want to use a microcontroller, which is an example of an application specific processor, or do you want to go single purpose computer. Now, I have an example where a particular application was implemented using these 3 approaches. The first one was implementation of a particular project, which is a roulette wheel game using 8085 microprocessor. This is the block diagram. If you see this, it has so many building blocks. One block, let us go from the left, you have the microprocessor, which is 8085 in this case. Microprocessor requires RAM and ROM, which are indicated on the middle blocks. These have to be decoded, the address of these devices have to be decoded. So, there is decoding circuitry, and then you need certain output ports to indicate the state of the game to the user. And so, for that we have 4 ports which is connected to 4 7 segment displays, few discrete LEDs, a buzzer and a ring of LEDs, 2 rings of LEDs to indicate the game that you are playing, that you want to place your bet and then you want to roll, you want to let the roulette wheel roll, and then it will stop, the speed of rolling will slow down and it will stop somewhere. If that matches with the bet that you have placed, you win, otherwise you lose. And this was implemented using 8085, and here is a schematic diagram. As you see, it uses so many integrated circuits. I also have a picture of the actual implementation. On the left you have a PCB where the middle top IC is the 8085 microprocessor. At the bottom you have a ROM and RAM. The ROM is in the form of a E2PROM, and you have these latches on the left and right, and on your right is the actual input output board where you see 2 rings of LEDs, the red and the green, and at the center you have the 7 segment displays. And obviously, as you see, it uses far too many ICs. My students implemented the same design, same application using a microcontroller. This is the block diagram of a Arduino, which is a microcontroller. Basically, Arduino uses AVR microcontroller. This is an application using Arduino, and you can see this block diagram. You see suddenly the number of blocks have reduced. Why? Because the microcontroller has integrated the microprocessor and memory and ports into a single chip, therefore, the size reduces. Here is the schematic diagram of the microcontroller based roulette wheel. As you see, the components have reduced, and here is the photograph. As you see, you have a very small PCB on your left, which is just one microcontroller, a switch and so on, and on your right you still have the LED rings, red and green, and the 7 segment displays. This is the second implementation of the roulette wheel game. And then we also have the implementation using the single purpose computer implementation using a CPLD. CPLD stands for complex programmable logic device. This is a device that you can program to implement a custom circuit, and this is the block diagram. You see, this block diagram is split in two parts, which is exactly what we had discussed earlier, that it consists of a sequencer, which is the finite state machine in this case. The finite state machine controls the data path, where the actual operations, the processing of information, processing of data takes place. In this case, several building blocks of processing that data are being used. For example, this uses a counter, it also has a comparator for comparing the numbers that are being generated, and on the rightmost side you have decoders for controlling 36 red LEDs and another decoder for controlling 36 green LEDs, which would form the inner and outer ring of the roulette wheel. This is the schematic diagram. As you see, it has a CPLD and all these LEDs and all that, and you see there are almost no other ICs being used other than a clock generator based on a 555 timer IC. And here you can see the actual implementation, a single printed circuit board pretty much, which has the LEDs on the outer periphery, and at the center you have the CPLD IC. So, you see, it is possible to implement any embedded application in 3 ways: the general purpose processor approach, which usually involves many components. There may be some good reason for you to use that approach, but from the point of view of cost and reliability and economics, maybe you would want to implement the same application using an embedded computer, using a microcontroller. And the third approach, of course, is the single purpose computer, and there are many applications which are done using this approach. I want to show you how things used to be designed earlier in 60s and 70s, integrated circuits. On your left is a picture of design engineers inspecting the layout of an IC. You see, the IC itself is very small, probably millimeter square or a couple of millimeters or thereabouts, but you can't inspect the design on such a small piece of substrate, and so you blow it up by several magnitudes, and then it occupies almost a big room, and you see these design engineers are inspecting the design. And today you do not have to do that at all, because you are using CAD tools and languages which are designed for design, which are created for implementing and designing hardware. And so, on the right you have a synthesizable code to implement a 8085 microprocessor. Of course, this is just an example, and today you would not implement a 8085 microprocessor, you would implement whatever fancies you, whatever is in your mind, and you can use a language such as VHDL or Verilog to implement that circuit. Till this time we have discussed implementation of the embedded system from a processor, that is the embedded computer point of view, but that is not the complete story, because we would like to build a complete system. So, at a system level, what are the various approaches? It turns out that there are 2 popular approaches. One is that you build everything from scratch on your own, meaning you decide what embedded computer you are going to use. For that, what kind of circuitry is required, what kind of additional components are required. You would need a printed circuit board for that, you design it, you get it fabricated, and then you integrate all the components on that PCB. And usually you will take this approach when you are expecting large volumes, because you would benefit from economies of scale. But when your applications are not, when your requirements are not that large, volumes are not that large, there is a alternative method, and I call it COTS approach, that is components off the shelf, meaning you buy things that are available and you quickly integrate it and implement your design. And these days you could implement this COTS approach using popular single board computers, which are very powerful computers today, such as Raspberry Pi or BeagleBone Black single board computer. In the earlier times, or even today, if there is such a need, you would use a regular PC motherboard to implement what you want. So, we at this point we are at a stage where we have seen all these things you can do with embedded systems, how you implement the processor, how you implement the system. And I would like to now give you a small demonstration of MSP 430 based projects that have been designed in my lab, so that you the student, you the participant can feel confident that if my students can do it in my lab, you sitting wherever you are sitting can also design such systems. All right. So, let us have a look at some of these projects. For that, let me start with the simple project first. This is a project which is a battery-less electronic dice, but it has only one display. Oftentimes, you play a game where you need 2 dice, and so here is another implementation. This has 2 displays, and to use it again, this is battery-less. So, I will shake it, and when I stop, you see 2 numbers, 2 random numbers are being printed here. Again I shake it, when I stop it produces 2 random numbers. What does it use? It uses MSP 430 microcontroller. At the in the middle you have the a tube which produces which converts mechanical energy into electrical energy for the circuit to operate, and it on this side you have capacitors which store the voltage that is produced so that the circuit can operate. And you see this entire system has been fabricated in my lab. These PCBs have been fabricated locally, and the entire system has been integrated here. This is the second project. Continuing with the LED projects, here we have another system, we call it the color mixer, because it is going to mix 3 primary colors, green, blue and red, and create a custom color. I have the power supply for this comes with the help of in the form of this power bank. I am going to connect it to show to you. Now, this is how it works. I am going to reduce the colors. So, this is green, 256 levels of green, blue color again 256 levels, here again 256 levels of red, and I can add to certain levels of red, I can add certain amount of blue, and you see I get various shades of magenta, or instead of blue I can add green and I get various shades of yellow, or into this now I can add blue and I get various shades of white, and so on. And so, because this uses MSP 430 microcontroller, it controls these 3 LEDs using a concept called pulse width modulation that we are going to cover. And because each primary color has 256 levels, the total number of colors that can be made out of this color mixer are 256 cube, which is 16 million colors. This is the number of colors that can be made with this. Then I have this project which we call the electronic birthday blowout candles. These are supposed to be birthday candles, so that they function without using real candles. Real candles with small kids can lead to a fire hazard, and here so we have done away with real candles and instead used LEDs to mimic the function of a candle. Now, if these are candles or if these are mimicking the operation of a candle, then I should be able to blow them off like I can blow off normal candles, and that is the magic here. We have used a sensor, a thermistor, which will detect air blow when I blow on it. The microcontroller here is going to sense the air blow on the thermistor and will randomly turn these LEDs off. So, let me try, and as you see it is also making a sound, it is playing happy birthday sound. So, this works like a replacement to traditional birthday candles. It is perfectly safe to use any number of times you or your kid would want to. Let me show you another project now, and this is a electronic sand glass. So, instead of sand falling from one part of the sand glass onto the other side, here we use LEDs. As you see, as I am holding it, this is the LEDs indicate as if sand is falling. Now, if I turn this around, this sand should come to the neck, and you see now it is falling in the other direction. And normal sand glass, when it empties the sand, it does not say anything, but because this uses a embedded computer, it will tell you that the time has elapsed. Now, if I turn it around, again it is falling on the other side, and this has been programmed to empty the so called sand in about a minute of time. This also uses another MSP430 microcontroller, and the sensor for the orientation is also integrated in this project, and in fact it was conceived and designed in the lab. And this project actually, I will show you, this is the enclosure which was made in the lab using a CNC machine. This is the embedded computer here, this is the sensor part here, and it is being powered with two AA sized alkaline batteries. Let me show you another project, and in this case this is a kaleidoscope, LED kaleidoscope. Normal kaleidoscope has glass pieces in the form of bangles and 3 or 4 mirrors, where the external light is reflected, diffracted through the glass pieces, glass bangles, and you see multiple reflections through the mirrors. In this case we have done away with the natural light, and which means you can use it anytime you want, whether there is outside light or not. Inside there are RGB LEDs, several of them, and their lighting patterns change as you move it around. Why? Because we have integrated certain sensors in this, and of course there are the mirrors also, and an embedded computer MSP430. As you can probably see, as I am turning the kaleidoscope tube around, the lighting patterns inside are changed, and if you were to look through this, you would see interesting patterns. In fact, what I will do is I will share pictures with you of the close-up pictures looking through this hole, so that you can see how the lighting patterns look like. Now, I have another project. This is a slightly advanced project based on MSP430, and this is called Talking Tom. This is the hardware implementation of a Talking Tom application you may have seen on a mobile phone. What this does is, on what that application does is that it will record your sound and then it will play it back at higher pitch. So, this project we call Talking Tom. We actually call it Talkative Tom because we did not want to have issues of copyright names. This does that, and it also adds another feature that in a second mode it can play back the recorded sound, and it will sound like an alien. So, let me give you a demonstration of that. I have 2 selector switches here with which I turn it off and on, and with the other switch I can select the mode. In this case I have selected the high pitch mode. Hello, this is the project demonstration of Talkative Tom.
Hello, this is the project demonstration of Talkative Tom.
Let me change the mode and make it the alien mode. Hello, this is the project demonstration of Talkative Tom in the alien mode. The entire enclosure was fabricated in the lab. As you can see, the circuit board was also fabricated and soldered in the lab. It has integrated battery source, charger, and audio amplifier and speakers. And last but not the least, the project I am going to show you is what we call as the levitating doll. I am going to power it with a adapter, 12 volts adapter. In my hand is a 3D printed doll, and in the hat of the doll there is a small magnet. There is a microcontroller on top, and here I have a electromagnet. At the bottom of the electromagnet there is a Hall effect sensor which senses the position of this magnet when I hold it there, and the microcontroller will maintain the position of this doll suspended in the air. Let us see how it works. You see, it is floating in the air. Why? It is sensing the position. If because of gravity the doll tries to fall, it turns on the electromagnet. If the doll tries to come too close, it turns off the electromagnet, and this operation it is doing thousands of times a second to maintain the position at a given location. and all these are implemented by my students using MSP430 microcontroller. And so, if my students can do it, I am very sure you as my remote student can also do it. Thank you. We are going to continue our next lecture and talk about other issues related to embedded systems, but at this point I would like to summarize what we have discussed here. We have gone through various definitions of embedded systems, we have seen application areas of embedded systems, we have seen how embedded systems could be implemented using a general purpose processor or a application specific processor or using a single board computer. We have seen what are the characteristics of embedded systems, and at the end we have seen some applications which I hope you found to be very encouraging. Thank you very much, and I will see you in the next lecture. Bye bye.